In this lesson, I'll show you several examples on how to transform linear absolute value equations. Just a few short words before we begin. A translation is a transformation that shifts a graph horizontally or vertically, but doesn't change the overall shape or orientation. Let's say we're given y is equal to the absolute of x. This equation can be translated using two numbers, namely h, that's applied within the absolute, and k. K is responsible for shifting it vertically, while h is responsible for shifting it left or right. Another transformation can be a stretch or compression via the factor a. Notice that I've applied an a being multiplied to the absolute. When a is greater than 1 or less than -1, the graph gets skinnier, or vertically elongated, or vertically stretched, however you want to describe it. When a is between -1 and 1, the graph is vertically shrunk or compressed. Think of the value a as the slope. In addition, if a were negative, the graph reflects. With that being said, question 1 reads, graph the following function without making a table. As you can see below, we have y is equal to the absolute of x already graphed. In our first question, a, we have y is equal to the absolute of x minus 2 plus 3. In this equation, h and k are introduced, but there's no factor of a at the front. Another way to read this is to say the absolute of x minus positive 2 plus 3. Notice that this expression and this expression mean the exact same thing. Negative times positive is a negative. The reason why I'm writing it out this way is because now h is positive 2 and k is 3. This means that we'll be shifting the graph vertically upwards by 3, because this is positive, and because 2 is positive, we'll be shifting that point to the right by 2. Another way to think about it is that if it's negative, you go to the right, and if it's positive, you go to the left. This is the reason for it. So with that being said, let's start with this point. We'll go up 3, 1, 2, 3, and then shift it to the right twice. So our new vertex is right there. Also take a look that because the original y is equal to the absolute of x had a factor of a of 1, that means the slope was 1. And slope is rise over run. So we can write down 1 as 1 over 1. That means that we go up 1 over 1, up 1 over 1. And we're going to do the same thing for ours. Up 1 over 1, up 1 over 1 again. And you do this for here and for the other side as well. So what you see me hovering over is your transformation for a. Let's move on to b. In b, we have y is equal to 1/2 times the absolute of x. As mentioned above, when your a value is between -1 and +1, which applies here, we have 0.5. Then it gets fatter, or it vertically compresses. So you're going to expect the original to be wider. To show this, let's take for example this point. Because this is 0 and 0, we can forget about it. But let's take for example that point. That point currently is at 1 and 1. The x stays the same for the transformation because there was no h applied to the equation. Whereas the y, it gets halved. It becomes 0.5. Let's take this point. We have 2 and 2. Once again, the y gets halved, and we'll keep 2. So 2 divided by 2 is 1. Let's take another point. Let's take this. We have 3 and 3. Dividing 3 by half gives you 1.5. Let's plot these points. This new point will be just underneath. This point will be here. This point will be halfway, and now you get the point that it's always half of the y that you had initially. Because it's symmetrical, we should expect the same thing on the other side. If you connect these points, you should end up with a graph that looks like this. What I'm hovering over is the graph for b. Now the opposite is true for c. This time we have a factor of 3 over 2, which as a decimal number is 1.5. So it's now greater than 1. And when we have numbers that are greater than 1, we expect it to get skinnier. So let's take these exact same points, the original points, and rather than multiplying 1, 2, and 3 by a factor of 1 over 2, I'll multiply them by a factor of 1.5. So we get 1 and 1.5, that's our first point. Over here, 2 times 1.5 is 3, so 2 and 3. 3 times 1.5 is 4.5. And let's plot these points. Let's see how it changes. And just to make things easier to visualize, I'll erase the first one that I created. There you go. So starting with our first point 1 and 1.5, we have a new point right here. Then 2 and 3 is up here. 4.5 is over here. And the same thing is true for the other side. Of course, the origin will remain the same because we don't have an h and a k. If I connect these, you should end up with the following. What you see in black represents c. Finally, in D, we have the factor a, h, and k. This time, our h should be negative 2, because think of it this way. X minus negative 2 in absolutes is the same thing as plus. So it's negative 2 and negative 3. This means that we'll be moving everything to the left by 2 units and everything vertically downwards by negative 3 units. And then we'll multiply by a factor of 2, so it will get skinnier. Take, for example, this point right here. This point will go down 3, 1, 2, 3, and it will be shifted to the left, 1, 2. Now that we found our new vertex, if we didn't have this factor of 2, you would have another point right here, and so on. So to apply this factor of 2, let's take a look at this point. That point is at currently negative 1 and negative 2. Just as before, we'll multiply the y coordinate by a factor shown here, which is 2. We end up with negative 4. But also there's this k. What you do is you reverse its sign. Right now it's negative 3. You make it positive 3, and you add it to the negative 4 that you just found. Negative 1. So your new point, rather than negative 1 and negative 2, will be at negative 1 and negative 1. So your new point should be right here. Similarly, to get the next point, this would be what it would be originally, which is at 0 and negative 1. Multiply negative 1 by the factor 2. You end up with negative 2 plus 3 is positive 1. So your next point would be at 0 and positive 1. I'll erase what I did before just to give you a better visual. And now I will connect these dots that I just created. Now, interestingly, what some teachers like to do is they like to apply this transformation first, the 2, and then apply the h and k numbers. So it's strictly up to you which you would like to do first. Let's move on to question 2. Write an absolute function that is stretched by a factor of 3. So I'll start with y is equal to the absolute of x. If it's stretched by a factor of 3, that means it's getting wider. So this is 1 over 3. Reflected about the x-axis. If it's reflected, then the factor a will be negative. So y is equal to negative 1 over 3, the absolute of x. Moves 3 units to the left. If it's moving to the left, then we'll say plus 3. And 2 units downwards. The downwards suggests that the k is negative. Another way to interpret this stretch part here is that if it's vertically stretched, then this would be a factor of negative 3. If it's horizontally stretched, then it's negative 1 over 3. That means it's getting fatter, whereas this one is getting skinnier. And there you have it. That is how to transform linear absolute equations.